Let's work on a practical application of inverse variation. So in this table, the math class has decided to pick up litter each weekend in a local park. Each week there is approximately the same amount of litter. The table shows the number of students who worked each of the first 4 weeks of the project and the time needed for the pickup. So clearly, the more students you have working on the project, the less time it's going to take to do it. So this seems to suggest inverse variation, because anytime one quantity is going up and the other is going down, that would be inverse variation. If you're concerned about whether or not it's inverse variation, plug the top row into list 1, the bottom row into list 2, and do a stat plot. Remember, in order to do a stat plot, you need to make sure that stat plot is on. That's under second y equals. And then go to zoom and find zoom stat. And you should get a graph that looks similar in shape to this. And that graph seems to suggest inverse variation. All right, so we've decided this is probably going to be inverse variation. So if it's inverse variation, it must be y is equal to k over x. Well, in this equation, we're not going to use x and y. They used n and t. N is the equivalent of your x, and t is the equivalent of your y. So t is equal to k over n. So in order to find the constant of variation, we're going to have to multiply our n's and k's. So I'm going to do that up in the actual table. So to find the constant of variation, you do 3 times 85, which is 255. 5 times 51, which is 255. 12 times 21, which is 252. And 17 times 15 is 255. Now, not all of the products were the same, but that's okay. 252, even though it's not 255, is awful close to 255. And in the real world, data is never perfect, but it has a suggestion of an inverse variation. So therefore, we're going to say that the equation that best represents this data is t equals 255 over n. And it will give us a good estimate as to how long it will take us to clean the litter based off the number of students we have. What if I said instead that I want to find out how many students I need if I want to try to finish the job in 30 minutes each week? Well, if I want to finish this job in 30 minutes, then I would need to find the number of students t. Sorry, not the number of students t. Let's try that again. If I know that t is 30 minutes, let's try this again, then I would solve this equation for n, because I need to know the number of students. Now, remember that one of the things we could do was we could rewrite it like this, which was Tn is equal to k. So n must be equal to 255 divided by 30, which is 8.5. Well, you can't have 8.5 students, so we probably need about 9 students showing up every week in order to be able to clean the litter in approximately 30 minutes. Sometimes we have equations that combine both variations, both direct and inverse. When we have more than one variable being multiplied by the constant of variation, we're going to call that joint variation. Joint variation really is just direct variation. So if I said z is equal to k times x times y, Since there are two quantities being multiplied by the constant, we say that z varies jointly with x and y. Sometimes they'll say with the product of x and y. It really doesn't matter. Well, now I'm going to tack on this. What if I give the equation z is equal to kxy over w? Well, z still varies jointly with x and y because they're being multiplied by the constant. But the w is in the denominator. So we're going to say, and inversely with w. Anytime you have a variable underneath the constant, that's inverse variation. Variables next to the constant, that's direct, or if there's more than one variable, joint variation. I'm going to change this equation just a little, and instead I'm going to have one variable with the constant, being multiplied by the constant, but I'm going to put two variables in the denominator. So now I'm going to say that z varies directly with x and inversely with w and y. And the reason this is important is because we're going to talk about an equation where we're going to have multiple variations. Let's do a combined variation problem where we have to write an equation and then use it to find a value. The number of bags of grass seed N needed to reseed to reseed a yard. I shouldn't have put this. Hold on. I'm fixing this. The number of bags of grass seed N needed to reseed a yard varies directly with the area A to be seeded and inversely with the weight W of a bag of seed. If it takes two 3-pound bags to seed an area of 3,600 square feet, how many 3-pound bags will seed 9,000 square feet? All right, first of all, they told me that it's direct variation with A. So the number of bags N is directly variated with A, but it's inversely variated with W. That means A is being multiplied with the constant, and W is being divided into the constant. So we start with this general equation, N equals Ka over W. Well, then they gave me some information that I can use to find the constant of variation K. They told me that if it takes two 3-pound bags to cover an area of 3,600 feet, and the weight of the bags are 3 pounds each. Now I can solve this for K. So in order to solve it for K, it's really just a proportion. So I'm going to multiply 2 times 3. And then I'm just going to rewrite that as 3,600 K. And then I would divide by 3,600. And I'm going to find out that K is equal to 1 over 600. So now I know the equation is N equals, we would write 1 over 600, and then it's A over W. That's not quite how the book writes it. The book writes it as A over 600W. But sometimes we forget that the constant can be a fraction. So in this case, the constant is 1 over 600. That will come back to haunt us on the unit exam. All right, now that I know my equation and my constant, now I can go back and find out how many 3-pound bags I need for 9,000 square feet. So now I want to find N if A is 9,000 square feet, and the weight of the bag is still 3 pounds. So I'm going to get 9,000 over 1,800, and that's going to reduce to 5. So it's going to take 5 3-pound bags of seed to do this lawn. Let's do another real-world application. This one applies to physics. Gravitational potential energy, PE, is a measure of energy. PE varies directly with an object's mass m in kilograms and its height h in meters above the ground. Physicists use g to represent the constant of variation, which is gravity. A skateboarder has a mass of 58 kilograms and a potential energy of 2,273.6 joules. What is the gravitational potential energy of a 65 kilogram skateboarder who is 4 feet above the ground? First, I have to write an equation to represent the situation. So let's go back up here. We said that the potential energy varies directly with the mass and the height. And G is going to be our constant instead of K. So that means I'm going to use the equation PE is equal to GMH. Because direct variation means that my variables are being multiplied by the constant. All right, now that I have an equation, the next thing I need to do is use the given information to find out what G is. So I know that the potential energy of a skateboarder is 2,273.6 joules. I don't know G, but I know the mass of the skateboarder is 58 kilograms, and the skateboarder is going to be 4 meters above the ground. So we're going to solve this for G. So we're going to multiply these two. So I get 232G is equal to 2273.6. And then I'm going to divide by 232. And we're going to find out that G is about 9.8. And if you know anything about the gravitational pull, G, that we use in physics, it is 9.8 meters per second squared. All right, now that we know that G is 9.8, now I know my equation is PE, for potential energy, is equal to 9.8 times the mass times the height. So now if I want to find the potential energy of a 65 kilogram skateboarder who's 4 feet above the ground, 4 meters, sorry, now I'm going to use 9.8 times 65 times 4. And I'm going to find out that it's 2,548. And the unit of measurement for potential energy is joules.